Hello. Hello, could you please confirm that you can see the presentation? Hello?
Yes, sir.
Yes, sir,
Okay.
we can see the presentation.
Thank you. Okay, so let us start now. I touched upon some of these points in the last class, so I shall briefly go back to those points and have a quick revision. In the last class, we began the discussion on electromotive force. So prior to that, we had finished discussing the Maxwell equations, both in electrostatics and in in magnetostatics. Electrostatics as in charges are fixed. Magnetostatics as in that the current producing the magnetic field is a steady current. Now we shall move beyond statics, and in order to do so, we shall have to understand the idea of an electromotive force. So let us try to see what is it. We begin with a simple discussion, namely that of a current in a loop. So here's a conductor left to itself. Even if there was a loop left to itself, no current would have flowed. So you would have had to create a potential difference across the conductor along the whole length of the conductor, because of which current will flow. Now the potential difference could be done in so many ways. I mean, you can use a battery. There are so many other ways of creating a potential difference, such as a thermocouple, piezoelectricity, all sorts of things. But here I'm not exactly referring to the mechanism behind creating the potential difference. Here it is just a battery, but it could be other means, and those other means shall be important for us later. So let us see. As soon as you create a potential difference, consider a charge in this conductor which is moving. Remember, after all, to conduct a current in a conductor, you have to make charges move. All right. So to make charges move, you have to create a potential difference. Electric potential difference, of course. For instance, in mechanics, you have to create, let's say, in gravity, you have to create a gravitational potential difference under which masses will move. So here we are creating an electric potential difference and charges will move. So as soon as you have moved a charge, well, to make something move, which that something which was earlier static, you need to apply a force on it. So what is the force that you have on a charge? So on a unit charge, a single charge in this current loop of unit value, let us say 1 coulomb, a single charge, it will experience a force of F subscript S. S as in source, F subscript S. Now let us try to see what happens. Now these charges are moving. Now here, just concentrate where I'm placing the cursor. Here, there is a bend in its path. It could very well be that there will be a traffic jam over there. For instance, on a busy road during office hours in the morning, at large crossings where a lot of cars crisscross, you experience traffic jams. So you have traffic lights and the police are alert, something like that. So charges are moving, but here at this bend, suddenly there has been a buildup of charges. Let us now try to see what happens. I've written something over here, local field buildup. Now, overall, this conductor, this wire is charge neutral, overall. But suddenly here, and remember, when we are talking about current, we are thinking precisely the flow of positive charges. Although in reality, let us say in a copper wire, the reality is that the electrons travel. But by convention, we have defined a current to be a flow of positive charges. So although electrons actually travel and conduct a current, we say that conduct the opposite of a current. We say that a current is an equivalent flow, a hypothetical flow of positive charges in the opposite direction. That is how we understand it. So let's say positive charges have moved and they have suddenly built up over there here. So it's just like cars have suddenly gathered at a traffic crossing or at a bend in the road. And so what will happen? Suddenly there's an imbalance of charges over here, more positive charges than there should be, positive charges which are current carrying, which are conducting the current. And if suddenly there's a pocket of excess positive charges, there will be a local electric field, because remember, charges will always have an electric field with them. An electric field must arise due to a charge. So you will have a gathering of positive charges, and accordingly you will have a local field buildup. What will happen now? So positive charges tend to throw field lines outwards. Try to follow this point carefully. Positive charges tend to throw field lines outwards. And there are now, what will happen here? There will be a traffic regulation. More charges will be coming from this side, but if there is a pocket of positive charges over here, which is throwing a field line in the opposite direction, they'll be throwing field lines in every direction, outward field line in every direction. So charges which will be coming into the region, they will be prevented because they are also positive charges. So they will be resisting the arrival. So this local pocket of positive charges will be resisting the arrival of excess charges in the current. Meanwhile, there will also be some charges which are moving slowly ahead. Otherwise, the traffic jam would not have happened. So those charges will be pushed out by the outward going field line in the pocket. So what will happen is that this will become a self-regulatory traffic control mechanism. What do I mean by that? That this sudden local buildup of positive charges will push slowly moving ahead charges outward more quickly so that the road is cleared, and it will resist the arrival of further positive charges from this side. So on this side, the slowly moving charges will be pushed out. On this side, further incoming charges will be resisted, just like a red light in a traffic resists the arrival of further cars. If you have a traffic jam, or policemen will blow the whistle and stop the further arrival of traffic, something like that. So there will be a self-regulatory traffic mechanism over here, as a result of which this local electric field E will balance out the charge buildup or charge difference quite quickly, almost instantaneously. Okay. So basically, if you were a charge in this loop, you can feel, if you are a unit charge, if you were a unit charge on this loop, in this loop, you will feel two kinds of forces. One, due to the potential difference of the battery, which is Fs, total force on a unit charge, F is equal to Fs. That is always there. And the other is that occasionally there could be little pockets. It's not a very smooth road. So there could be little pockets of charge buildup, and they will balance out these charges very quickly, but you will nevertheless feel that force also. If you were a charge of any other, if you were a charge of any other value, let us say Q, then the force that you would have experienced, I mean, this is actually electric field. Force on a unit charge is exactly the electric field, value-wise, right? So, because force is charge into electric field, F is equal to Q into E. So on a unit charge is just F E, you're just putting a 1 here all throughout. Anyway, so as I've written over here, Fs is due to the source. It's the force due to the source, a battery in this case. Now let us try to see what electromotive force is. Electromotive force, I'm defining it by E, but I'm writing it slightly differently. This E is the electric field vector E, whereas this is a scalar field E. You can immediately see there is a little bit of a nomenclature problem over here, a naming problem. We shall see about that. First, let us define this quantity E as the closed path integral over the entire loop of this force F on a unit charge. F, force, small f, force on a unit charge, F dot dl. F dot dl. Okay, and what is F? F is can be decomposed into two vectors, Fs plus E. So basically F I'm writing as E plus Fs. So E dot dl plus Fs dot dl. So I've broken this integral into two parts. Okay. Now, what is E dot dl? E is the electric force due to these instantaneous charge pileup. Little charges have suddenly gathered and they have created their electric field. But that electric field, you know, when you integrate an electric field over a closed loop, static electric field over a closed loop, it will be zero. So this is due to the smoothing effect that you have. Okay, therefore, this Roman upright E, so this part will vanish, E dot dl, that will vanish, and so you are simply left with the Roman upright E will be equal to Fs dot dl. This thing is defined as the electromotive force. Once again, I stress this is not to be confused with this E. This E is the electrostatic field. The electrostatic field, as has been written over here, this E is the electrostatic field that has been created due to a local charge buildup. And if it's an electrostatic field, E dot dl will go to zero. Okay, so then what is this Roman upright E? That is Fs dot dl. Now, if you look at it, Fs, what is Fs defined as? Fs is defined as the force on a unit charge due to the potential difference created by the source, a battery, let us say, right? Fs. So Fs is due to the source. So basically, this is a force on a unit charge, force dot dl. And what is force dot dl? Work done. So basically, the electromotive force is to be understood as the work done on a unit charge. Follow very carefully. Work done on a unit charge by the source, Fs. That's why it has been underlined, stressed, Fs, in making it go round the loop. So you make a unit charge go round the loop, the unit charge will go round the loop because of the force imparted to it by the source, or maybe equivalently you can see it as the potential difference created due to the source. If you have a potential difference, immediately from there you can find the force due to it. So because force is the negative gradient of a potential function, don't forget that. So you under the effect of the force due to the source, a unit charge will go round. So when you apply a force and make something travel through a path, a displacement, then you will have some sort of work. And what is this work? This work is the electromotive force. So immediately you can see this E, although you are calling it electromotive force, it is not a force at all. It is work done. It's a scalar quantity. Work done is energy, energy expended to make the charge, or energy required to make the charge go around the full loop. So it is a form of energy, although we are calling it a force. Actually, we are in a historical era here. Historically, it is called the force. I mean, the time when these names were thought of, the ideas were not very clear even to the early discoverers or the experimenters or the scientists. So that's why there's a bit of a confusion about the terminology. As you can see, I mean, we have a lot of confusion about various things. Two very simple things stand out over here. First, what is a current? Current is a flow of positive charges. Fine, but later discovery tells us that positive charges are not in motion. It's the negative charges that are in motion. Therefore, to stick to the convention, we say that a current can be thought of as an equivalent flow of positive charges opposed to the direction of the flow of negative charges. That's number one. And number two, here we have another example. Although we are calling something an electromotive force, it is not actually a force. It is work done, a form of energy. What is that energy? Energy required to make a unit charge go round the circuit completely, and the energy is imparted by the source over here, which may be a battery, which may not be a battery. Okay, anyway. So with this idea of an electromotive force, this is the basic idea of an electromotive force. Now we shall go to the idea of what happens when a magnetic field is changed. Remember, we talked about earlier in the last class, we talked about magnetostatics, a constant magnetic field. A constant magnetic field is produced by a steady current. Here, we are now beginning to talk about a changing magnetic field. So we shall no longer hereafter be talking about statics, but dynamics. But before that, we will keep our initial discussion quite simple. And let us first try to have an understanding of the diagram that we have here. Let us try to understand the meaning of this diagram. So here is a shaded region with all these inclines. Follow the movement of the cursor carefully. Here is a shaded region. A magnetic field is drilling into this shaded region, going into this. So as you are looking at your screen right now, what you shall see is, I'm sorry, just a minute. Sorry, can you please just confirm that you can hear me clearly? Hello?
Yes,
Yes,
sir.
sir.
Okay,
Yes,
okay.
sir.
Thank you. Please mute your mic. Thank you very much. So, as you're looking at the screen, the magnetic field lines are going away from you and entering the paper normally, the plane of the screen normally, perpendicularly. This circle is meant to indicate that. It's like, this is if you shoot an arrow from a bow, and if you look at the arrow from behind, I believe that you are aware of what an arrow looks like. It has got a pointed tip, and at the other end, it's got a feathery tail. So this is the end part. You're looking at the feathery tail from the behind, so it would look like a fluffy cross-like thing with a circle around. I mean, basically it is like that. I mean, the arrow is going into the plane of the paper, so it is into the page. This is the back part of that magnetic field arrow. So this is just going straight into the plane of the paper through this shaded region only. Okay, fine. Now, here we have a square copper wire loop or any good conducting wire loop. It's square in shape. Of course, if it's made up of any simple material, it will have some resistance. Even very good materials offer a little resistance to the flow of a current. So it has some resistance R. And that's not really very important. The height of this copper wire is h, right? So this height is h, and the portion that overlaps, the portion of this wire that overlaps this shaded region has a width x. So this area over here, coinciding, area of the square loop that is coinciding with the shaded region is h in height, x in width, and so this area will be h into x, hx. So this shaded region of the wire, shaded region of the wire and the magnetic field overlapping will have the area h into x. Only this part. Follow the cursor. Okay. Now, let us see what happens next. Let us say you are an experimenter. You are standing on the right hand side and you have pulled this wire to the right. So this wire will now, so this wire loop, you're holding it here with your hand and you've pulled it to your right. So this wire loop will move to the right with a velocity v. The arrow over here indicates the movement of the wire to the right with a velocity v. Okay, now comes something important. Follow the discussion extremely carefully. Uh, uh, this copper wire is full of charges, let's say so-called positive charges. Actually, it is full of negative charges that can move, but let's say it's full of positive charges that can move. So suddenly it is moving, this wire is moving with a velocity v in this direction. There is a magnetic field. Follow carefully. The velocity v is from the left to the right as indicated by the arrow. The magnetic field is going from u into the plane of the paper, into the page, perpendicularly. So the magnetic field is drilling into the page and the velocity v is going to the right. So these two vectors, the magnetic field vector and the velocity vector, are perpendicular to each other. But we have already seen for ourselves what is the formula of the Lorentz force. Lorentz force is Q into V cross B. So if Q were to have unit value, unit charge, force on a unit charge, as you shall see, the force, how much will that be? So it will be V cross B into 1, Q into V cross B. Q is 1, so it will be V cross B. The magnetic force experienced by a unit positive charge in this copper wire will be V cross B. Now let us see. So if there is a force, then under the influence of this force, the static, so far the charges were static, they will start moving. But now let us see which direction will they move. Only the part of the wire starting from here, going this way, or maybe I should do it the other way around. Starting from here, going to the left, going up along this branch, and then going up to here. Only the part of the wire that is overlapping the shaded magnetic region will have the charges experiencing the force. Outside this shaded region, there is no magnetic field, and therefore the charges on this side will not experience any force. Okay, very good. So, if the charges are experiencing a force, they will start moving. But consider a charge on this branch or on this branch. What is the direction in which the force is acting? If this is V, going from the left to the right, and B is going straight into the plane, both are perpendicular to each other, then V cross B will produce a force that will go vertically up above in this direction as indicated by this arrow. The force that will be experienced will be going above, up above, in the upward direction. But a charge over here and a charge over here in the horizontal parts of these two branches, charge here and a charge here, will not be able to move upwards because they must move within the conductor, not out of it. So the charges here and here will experience a force in the perpendicular direction to the path that they are allowed. So they can't move this way or that. However, charges in this vertical part, they can very well move forward. So under the influence of the force, the charges in this branch only will have the freedom to move forward. But even as they move forward, they'll be pushing all the charges ahead of them. This is just like a train carriage that is pushed from behind. Sometimes you would have seen in railway shunting yards, you may have seen that large, long, very long rake goods trains, they travel in the opposite direction to the end of the engine. So the engine goes into the reverse gear and pushes all the carriages forward. Sometimes it does. It doesn't happen in the case of passenger train. In the passenger train, the engine is always pushed from the front. But occasionally, if they have to adjust wagons and all that, so it is basically something like that. These charges here will start moving. As a result, they'll be pushing forward all the other charges ahead of it, and they will be pushing the charges ahead of it. And as a result, a current will start flowing in this wire. Simply, follow carefully, simply because of the action of somebody pulling the wire to the right-hand side. You have a wire full of positive charges. This part of the wire will have the charges experience a Lorentz force, a unit charge on this part of the wire. Under the influence of that force, whose value is V cross B, the charges will move forward. Okay, let us now look at the magnitude of the force. What is the magnitude? V cross B. V and B are perpendicular to each other. So it will be V, magnitude of V times magnitude of B times sine 90 degrees. Perpendicular because V is going from the left to the right, and the magnetic field B is going into the plane of the paper. If that is so, and then there will be the vertical direction, but we are not exactly worrying about the direction. We're just keeping the magnitude. Now, current has started flowing. What is the source force that has caused this current? Like here you had a source due to a battery. Here, the source is this motion and the magnetic field. So this is the source. Incidentally, you will say, who is doing the work then? I mean, where is the work coming from? Well, the work is actually energy is being supplied by the person who is pulling the wire to the right. Anyway, let's not worry about that. Here I've written that over here. Work is done by the moving agency. By moving agency, meaning anyone or any machinery or whatever is pulling this wire to the right. You can get a detailed discussion of this thing in the Griffiths book, in the book by David Griffiths, section 7.1.3. Anyway, so what is the electromotive force? Let us see now. Electromotive force will be Fs dot dl In this case, Fs is the magnetic force on a unit charge, F mag that you have, dot dl, and then you integrate over the whole loop. Now let us try to see what is the outcome of that. What is the outcome of this integral? You have to integrate over the whole path. Okay, so on this side there is no force. So along this path, outside the shaded region, the integral will give 0. What about this part of the path, this portion? The force is acting in the vertically upward direction, and this path is perpendicular to it, so is this path. So when you want to take the dot product of the force which is going upwards and this path is perpendicular to it, the dot product between the two, remember what is the definition of a dot product? Magnitude of first vector times magnitude of second vector times the cosine of the angle between the two. Here the cosine of the angle will be 0 because it's 90-degree angle. So this part will also contribute nothing because the force and the path are perpendicular to each other. Same with this bottom path. So basically you will only get work done for this path, this vertical path along the entire circuit. Only the work done, non-zero work will be done over here. And what is the value of that non-zero work? Force, the magnitude is V into B, VB, and the path length along this vertical branch is H. So force into displacement on a unit charge will be VB into H. That is the electromotive force. This is the work done by the moving agency on a unit charge. Okay, so that is something we have seen, that a changing magnetic field can cause a current. What do you mean by the changing magnetic field? Let us now try to see. Define magnetic flux. Capital Phi, Greek phi, subscript m as in magnetic, is equal to, what is the definition of a flux? B cross a B into the flux of a field passing through a certain area. So this is the area dA. This is the area through which the magnetic field is passing. So in the rectangular section that coincides, the rectangular section of the wire that coincides with this shaded region, over that area, what is the magnetic flux? We shall have to find that. So in the rectangular section dA here, this part will have the area h into x. It's a rectangle, this part. Length into breadth. Length is h, breadth is x. So that part will have x into h. And so B dot dA, the magnetic flux, this thing, magnitude-wise, the magnetic flux is not changing. So B dot dA, the B magnitude of B will be fixed. So we can just simply take this integral to be the magnitude of B dot dA. dA has the whole area xh, B xh. B has got a constant magnitude, therefore it's not going to change anywhere within this integral. So you can just simply multiply B with the area of the rectangular cross section, B xh. That is the magnetic flux. Now we shall take the time derivative of this thing. d phi m dt is equal to bh dx dt. You see, B has got a constant magnitude, so we don't have to worry about its derivative. This h over here has got a constant height. That is also not changing. As you're pulling the wire loop to the right-hand side, only this x is changing. As time is increasing, this x value is decreasing because this loop is going to the right. If that is so, then x is decreasing with time. As time is increasing, x is decreasing. So dx dt will be a negative quantity. Dx dt, x will decrease as time increases because this length or this width will reduce as the wire is going to the right in time. So dx dt will be negative. H is a constant, B is a constant, so they will not participate in this derivative process. So d phi dt, d phi m dt will be bh dx dt. And what is dx dt? Dx dt, the value of it is the speed with which the wire is being pulled to the right. Someone is pulling this wire, some agency, machine or human being, whatever is pulling this thing to the right with a certain velocity v. And what is the value of that velocity? Dx dt. Dx dt is equal to v, and this minus sign I have forcefully written here. So negative bhv. Okay, and so d phi dt is equal to E. Why so? This is the E, E as in the electromotive force, which is not a force. Once again, I stress, it's the work done. E is equal to VB into H. So this thing is minus Roman upright E. d phi dt is equal to minus E. I've written something over here, and I've given a hint over here. Since, of course, the flux decreases and there's a minus sign, but I think you should know the answer. Why the negative sign? There is something called Lenz's law. Faraday's law and Lenz's law. I hope you have studied this thing at school. I mean, of course you have. So Lenz's law, what does it say? Simply put, it says that the induced current will flow in such a direction that the flux it produces tends to cancel the change. It opposes the change. The change in the current that is produced will tend to oppose the change that has changing the magnetic field that has produced the current. When I'm saying change, you follow carefully. The magnetic field is not changing in its value, but the magnetic flux is changing. Why? Because the area is changing. You see, X is reducing. If X is reducing, the area is changing, and therefore the magnetic flux is changing. What is flux? Flux is the total vector field passing through a certain area. How can you change the flux? You can change the flux either by changing the vector field or by changing the area itself. So here we are actually changing the area to make the flux change in time. So that is what it is happening. The negative side is due to Lenz's law. We shall see about this thing soon enough. I have mentioned the name of Faraday, and it is to his three very important experiments that we shall now go. So before I do that, I'm asking you to understand one thing very carefully in this diagram, that this current that was produced, happened because the wire loop was pulled to the right. And so somebody had done some work on this wire loop, and that work translated as the flow of a current. What is the amount of work done? The work done was, on a unit charge, the amount of work done was V into B into H. If V were to be 0, that is to say nobody pulled the wire is static, then there would have been no work done. V were to be 0, this Roman upright E would also be 0. Okay. And so would have been the rate of change of flux. Okay, so that is something that you understand. As time increases, flux is decreasing. Now let us understand Faraday's experiments. As I said, experiment 1, which we have just discussed, pulled the loop to the right. You pull the loop to the right, fine. You can immediately see that there will be, I mean, we have discussed it at length, why there will be a flow of a current. Some work will be done. Somebody will be doing some work on the charges by pulling them to the right. I mean, pulling this wire loop to the right. And as a result, there will be an effective Lorentz force. Now let us see experiment number 2. We can do 2 more experiments. What is it? Move the magnetic field to the left. Instead of, so you can see, ultimately, follow carefully, ultimately we shall have to change the magnetic flux. How can we change the magnetic flux? We can change the magnetic flux in 2 ways, either by changing the magnetic field or by changing the area of the overlap between the wire loop and the shaded region of this page. So what we have in the first experiment, we have done that thing only. We have changed the wire, pulled the wire loop to the right, and this shaded region, overlapping region reduced, and a flux change happened. Now we can say, well, let's not do that. We keep the loop as it is. We are not pulling the loop. We are pulling the shaded region instead to the left. That is the same thing as pulling the wire loop to the right. So maybe you have a magnet somewhere here in front of you, which is throwing field lines into the plane of the paper. And you have suddenly decided to shift that magnet to the left. And so this whole shaded region will also go to the left. In that case, also the area that coincides the shaded region and the square loop will change. Okay, so that is the second part, reducing the shaded area. Move the magnetic field to the left. Okay, move the magnet, that is, which is causing the field lines, producing the field lines, and those field lines are going into the plane of the paper. So we have shifted it to the left. So that will also cause. Now the third thing, I said we are interested in changing the flux. So instead of shifting either the shaded region to the left or the square current loop to the right, we are keeping both fixed. We are just changing the strength of the magnetic field. In this integration, we did not do that. We did not change the strength of the magnetic field. That is to say, we did not change the magnitude of the magnetic field, and the direction was also fixed. So that's why it was constant and we could pull it out of the integral. But now we are changing the strength of the magnetic field by, let us say, using an electromagnet. If you are using a simple static bar magnet or anything, that will not happen. But an electromagnet can cause a changing magnetic field strength. So basically, if the magnetic field becomes stronger in magnitude, then there will be more number of shades. You can imagine it, or you can imagine it in this diagram by drawing more number of shaded lines. Sparse shaded lines will indicate a magnetic field of weak magnitude. More dense shading on this part, in this part, will indicate a magnetic field of stronger magnitude. So we do all sorts of things. What are we doing? We are changing the area of overlap either by keeping the magnetic fields fixed, this shaded region fixed, and pulling the wire to the right, or second, keeping the wire loop fixed and pulling the shaded region to the left. Or the third thing, we are shifting neither. The wire loop is also fixed, the shaded region is also fixed. The only thing that we are doing is that we are adding more shading to this region. With the addition of more shading in this region, sorry, somebody's asking a question. I'll go to the question at the end. What is the source of the EMF and current in this, as that was the battery in the former case? Okay, we will come to that discussion shortly. That is the important question. It's there in the discussion itself. What is the source? Okay, so now, so you are doing all sorts of things to change the magnetic flux value. Fine. Here comes something very important. In all the things that you do, experiment 1, pull the loop to the right, keep everything unchanged. Experiment 2, pull the loop to the left, keep everything unchanged. Experiment number 3, pull neither the loop to the right nor the magnetic field shaded region to the left, keep both of them where they are. You just increase the density of the shading. In all of the cases, you observe that current is flowing. Current is flowing in all the cases. All the cases. This all is written in capital and it is a very historically famous all. How so? Let us see. Here. Let us try to understand this thing. It's a very important question now. And one of your friends has asked also, what is causing this current? In the first experiment, I have taken this to the right. The shaded region is fixed. Its shading density is also fixed. Okay. And we see a current is flowing. Fine. If current is flowing, something will have to provide the energy for the current to flow. I mean, if it did not have energy, it wouldn't have flowed. So what is causing this energy? I've written work is done by the moving agency. You have held this wire loop with your hand and your muscular force is contributing to the motion of the current. Follow carefully. If this velocity, now is the very important question. This thing is moving to the right, this wire loop. You follow, this is an extremely important question. This wire loop is going to the right. As a result, the charged particles in this wire loop, positively charged particles in this wire loop, have motion. If they have motion, there will be a non-zero value of V. And as such, V cross B will produce the force. This magnetic force is happening because the charges over here have had the velocity V. The wire loop is moving to the right, and as a result, with the having a non-zero value of V, the current has started flowing in the wire loop. Okay. But if this wire loop were to be static, this is the most crucial point. I ask you all to be extremely attentive on this question. If this wire loop were to be static, then V is 0. If V is 0, then the charges in this wire loop are also static, stationary, they are not moving. Okay, now what we see, we have not moved this wire loop, we have only changed shifted the magnetic field to the left hand side, as in the second experiment. Or we have just increased the shading in this region, as in the third experiment. Change the strength of the magnetic field, that is to say, increase the density of the shading. So in experiment 2 and experiment 3, we have done nothing with the wire loop. The charges in the wire loop are fixed. They don't have any velocity. Nobody is pulling the wire loop. The wire loop is as it is. And yet, when we tinker with the magnetic field, as we take it either to the left or we increase the shading of this area, we see that a current is flowing in all the cases, in experiment 2 and experiment 3. What is happening over here? Current should not be flowing because the charges are not moving. If the charges don't have any velocity, there is no question of experiencing a magnetic force. This V is 0 in all the charges. The wire loop is where it is. And if they are static charges, the charges in this wire loop are not shifting, and yet they are flowing as a part of a current, then it's not a magnetic something that is making them flow. Stationary charges current is flowing, of course, that is visible. Current can only flow when a force is pushing the charges. But this force can't be the Lorentz force Q into V cross B. Why not? Because V is 0. The wire loop is untouched. Nothing is moving the charges this way or that way. So, stationary charges are there in the wire and a current is flowing. There is only one way in which a stationary charge can experience a force. And what is that one way? To be subject to an electric field. A stationary charge, if it is subject to an electric field, will experience a force whose value is Q, which is the value of the charge, times the electric field, which is produced by an external source. For instance, you have a test charge of value capital Q. If there is no electric force anywhere in the neighborhood, the charge will be sitting where it exactly is. But if there is a source charge producing an electric field E, then Q into E will be the force experienced by the charge. So, the charges in this wire loop are stationary. Nobody has touched the wire loop or anything. You are just pushing the magnetic field this way or that way, or increasing the strength of the magnetic field, whatever you're doing. And as soon as you're doing that, you will notice that charges have started moving in this wire. You are wondering what is going on. These charges were static in me. They were static over there. I'm not doing anything with the charges. Well, so if they are stationary charges, static charges, they can only experience an electric field. You will be saying, I'm not doing any electric field business over here. I'm simply shifting around the magnetic field. I'm either changing its magnitude or I'm just reducing the area of overlap. Here is Michael Faraday's great insight. As you are changing the magnetic field, either by shifting the magnetic field to the left or by changing its magnitude, you are not doing anything to the wire. I have forbidden you, let us say you are forbidden to touch the wire. You're not doing anything to the wire. The charges in the wire are static, and yet as you are playing around with the magnetic field in the neighborhood, you will see suddenly the wire has produced a current passing through it. Where is this current coming from? Logically follow the chain of argument of Faraday. The wire had stationary charges. Nobody is touching the wire. And stationary charges can only experience electric field and nothing else. You have not produced any electric field in the neighborhood. You are only playing around with the magnetic field, either shifting the magnetic field to the left or changing the strength of the magnetic field. So, this is the conclusion. A changing magnetic field induces an electric field. See, if you had done nothing, if this thing were there, this thing were there, you're not shifting this to the left, you're not shifting this to the right, you're not increasing the shading or decreasing the shading, you're doing nothing of the so kind, then there will be no current. If you shift this loop to the right, there will be a current, but that can be explained because the charges have had motion and moving charges under a magnetic field will experience a force. Fine, that is also explained. But point number 2 and point number 3, they are very surprising. You are not touching the wire at all. You are simply shifting the magnetic field around, and the shifting of this magnetic field, either you shift the magnetic field to the left or you're increasing the density of the shading, that is causing a current. But the current shouldn't happen because the wire is untouched, the charges are static. What is causing the movement of static charges? Of course, it has to be an electric field, but you are not producing any electric field in the neighborhood. No, you're not. Or yes, you are. How? What is this yes, you are? You are producing the electric field by changing the magnetic field. That is the important conclusion of Michael Faraday, that a changing magnetic field will induce an electric field. And as you have changed the magnetic field, the induced electric field will cause the charges in this wire loop, which was stationary earlier, but stationary charges can experience only an electric field because if V is 0, there will be no magnetic field. But now the changing magnetic field has caused an electric field and they have started moving under the influence of this thing. Okay, very good. Einstein used this thing as a very important cue for his special theory of relativity. What is important? Now you follow the next point, although we shall not go beyond this next point, but that's Einstein's reasoning. What is important is not the absolute motion. In the first experiment, when you pulled this wire loop to the right, the loop itself had motion. That is fine. With respect to the background shaded region, it was moving. But suppose you do not touch the wire loop, instead you shift the shaded background region to the left. Then this moving to the left, this shaded region moving to the left is the equivalent of this loop moving to the right. What matters is not the motion of this thing in its absolute sense or this thing in its absolute sense. What matters is the relative motion between the two. Either this is fixed and this is moving, or this is fixed and this shaded region is moving to the left. That relative motion is important to cause the flow of current in the wire. And this was one great important insight that Albert Einstein had, extending Faraday's argument, with the help of which he created Einstein's special theory of relativity. And that's a different subject in its own. Not a different subject, really. Relativity is fundamentally founded on Maxwell and Faraday's electromagnetic theory, electrodynamics, electromagnetic theory or electrodynamics. Note, earlier, I used to mention two words, electrostatics and magnetostatics. But now we shall no longer call statics. We shall start talking about dynamics, because you notice this word, a changing magnetic field. The magnetic field is not static, it is changing. Therefore, you're talking about things that are changing in time, magnetodynamics, so to speak. Induces an electric field. Earlier, there was no electric field. Now, suddenly, because of a changing magnetic field, an electric field has been produced. So that is also a changing field. So this is all happening because of the relative motion between these two things. I've given a simple example, but this holds true in general. If you want to understand, have a greater, deeper understanding of it, I have written the section thing in this book, and you can also check up section 7.2, electromagnetic induction, in your book, David Griffiths. Anyway, I'll tell you all these things later. This experiment you can see in section 7.1.3, this whole discussion on the experiment. This is the fundamental experiment. This is a very basic discussion for a clear understanding of Faraday's fundamental thought process over here. So this page is actually a very important page. I mean, it should, I mean, the conclusions, observations and conclusions in this page should be considered to be one of the cornerstones of human
historical understanding of nature. Okay, with this now we go into some mathematical discussion. Faraday did not put all these things mathematically. He just gave the observations and gave the explanation in words. It was Maxwell who would put these things mathematically later. So we are beginning to get into that. I told you that electromotive force is Fs dot dl, closed loop integral. So here you have carried out experiment 2 and experiment 3. These two things have produced a current. Therefore, there must be an electromotive force. So what is the source force? Fs dot dl, electromotive force is Fs dot dl, closed loop integral. Now this Fs I'm writing as E. What is this E? This. We are looking at experiment 2 and experiment 3. In experiment 2 and experiment 3, the changing magnetic field has produced an electric field. And this electric field induced due to the changing magnetic field is producing the current. And this current going all the way around the loop will give you the electromotive force. Well, you should really be calling it the electromotive work, but historically it is known as electromotive force, EMF. You would have studied this thing. And electromotive force is also written as minus d dt of phi m. We have just discussed that thing here. E is equal to minus d dt of phi m. The minus is here. It will go to the left-hand side now. So this Roman upright E is minus d dt of phi m, which is the rate of change of flux. We are talking about changing flux over here. Now, let us see. d dt of phi m is equal to d dt of... Okay, follow carefully. What is phi m? Phi m is B dot dA. Earlier, B was fixed when we wrote this thing, but now B is no longer fixed. B is changing, either shifting to the left or changing its magnitude. So we can't really pull the B out of the integral. But we are writing d dt, phi m is integral, surface integral, B dot dA. This is the flux. Okay, now some mathematical discussion. We have discussed a good lot of physics. This part is the physics discussion. Now we discuss the mathematics. You notice that first we have carried out a surface integral, surface area integral, and then we have carried out a time derivative, ddt of the surface area integral. Integral first, derivative later. But here, what we are doing is that we have done two things. First, we have interchanged the integral and the derivative. Instead of taking the integral of B, surface integral of B first and taking the time derivative later, we are taking the time derivative of B first and the integral later. And secondly, here we had a full derivative ddt, but now we have a partial derivative del tau. Why? We have done two things. First, interchange the order of the integral and the derivative, and second, replace the ddt with del tau. Why have we do these? How could we have done these two things? What permits us to do these two things? Follow carefully. This is just simple calculus, nothing else. Mathematics, as I said. The physics part is done. The physics part is the great history-changing idea. A changing magnetic field induces an electric field. Now, that's Faraday part. Now we have to think like Maxwell. We have to do it mathematically now. I've put all these things. Faraday wrote it in English language. We shall have to write it in mathematics language. Here we are. I have given you a simple function, y is equal to x. Let's not worry about tau, t, and integral, all that. I'm giving you a simple function, y is equal to x. I'm saying, first you take the integral of x, and then you take the derivative of the integral. Or you take the derivative of x, and then you take the integral. Let's see what you get. First, you take the integral of x. What will you get? Integral of x is x squared by 2. Okay. Then you take the derivative of that integral. What will you get? 2x by 2. So you start with x, you integrate it, x squared by 2, then you take the derivative, you come back to x again. Or you go the other way around. You have x, you take its derivative. Derivative of x is 1. And when you have 1, you take the integral of 1 with respect to x, you'll get back to x again. So whether you take the integral first and the derivative later, or the derivative first and the integral later, it doesn't matter. It's the same thing. The outcome will be the same. I hope it's something like you have done in the early stages of vector calculus, where I said that you have a function that depends on two variables. Let's say psi as a function depends on x and y. You have you take del 2 psi del x del y, or del 2 psi del y del x. The order of the derivative does not matter, and so it is here also. Whether you take the integral first and the derivative later, or the derivative first or the integral later, it doesn't matter. You come to the same thing. So that is the first thing. Second thing is that I have got a ddt here, but here I have got a del del tau. Why so? You see, B now is no longer a fixed quantity in time. It is a changing field. So B is a function both of the spatial coordinates, as in x, y, z. That is why if B were not to be a function of the spatial coordinates x, y, z, you could have taken B out of this integral, but you can't. dA is an area element. It depends on x or y or z or x, whatever. So B is a function of the spatial coordinates x, y, z, but since we are also talking about changing magnetic field now, B is a function of t. Fine. So when you integrate this thing and put the limits of the integral, spatial limits of the integral, the outcome does not depend on the variable over which you have carried out the integration. You'll ask me, what do I mean by that? Simple thing. Once again, let us go to our simple example. I have asked you to integrate x. Okay. You integrate x and you get x squared by 2. Now I'm saying you put the boundary of the integral. Let us say integral of x, which gives you x squared by 2, going from the boundary values, limits, put the limits of the integral. Limits means boundaries, 0 to 1. What will you get? 1 squared by 2 minus 0 squared by 2. So basically you'll get half. So when you put the limits, because this surface integral requires you to put the boundaries, the limits of the integral, you have done all these things in all these charge density problem and all that kind of thing, or integral problems. So when you put the limits, the outcome that will have come out will be free of x, y, z. Follow carefully. When you put the limits to an integral, I just gave you a simple example. I integrate x, I get x squared by 2. When I put the limits, it will be, let's say, limits of 0 to 1. The outcome will just be half. Half doesn't carry any x, y, z business. We put the limits to the integral, it doesn't have any x, y, it doesn't carry the variables over which you carried out the integration. But here, B is a function of all the three spatial coordinates as well as time. When you carry out a surface integral or area integral with the help of the spatial, with the help of the limits, the outcome will be free of the spatial variables, but it will still contain time. Therefore, you write d dt. It will just be the outcome of this integral will just be dependent on time only. The spatial coordinates will go away upon solving this integral with the boundary condition. As a result, you will just have to take this outcome will just contain time as a variable, and you can only take, you can therefore comfortably take a full derivative d dt. But when you go inside the integral, follow carefully, you are now taking the time derivative first and the spatial integral later. When you take the time derivative first, B continues to depend on x, y, z, and t. So you're taking the time derivative first, but B still is a function of x, y, z, because you still haven't carried out the integration. If B is a function of x, y, z as well as t, you have to be careful. You can't just put a full derivative del d dt over here. You will have to put del del t to indicate that you are just taking the derivative only with respect to time and nothing else. So that is why you have changed it to a partial derivative. So two things have happened over here. It has taken us quite some time to express the idea. It's a mathematical discussion. I believe you would have studied this thing in your calculus course. I don't know. Two things we have done over here: interchange the order of the integral and the derivative first, and second, replace the full time derivative with a partial derivative del del t of B. Okay, so with that thing, d dt of phi m is integral, surface integral, there should be an s here, surface integral del del t of B dot dA. But then d dt of phi m is also equal to closed loop integral minus E dot dl. So this thing is this with a minus sign, and that minus sign I'm putting here. So E dot dl closed loop integral is minus d dt of phi m. And minus d dt of phi m will be minus del del t of b dot dA. Fine, we have got up to here. Then you can see we have got a line integral to the left and a surface integral to the right. You know of a mathematical method by which a line integral and a surface integral can be made the equivalent of each other, and that mathematical approach is Stokes' theorem. Curl of E dot dA, surface integral, is equal to E dot dl. Okay, E dot dl is minus del del t b dot dA. You just compare this with this, dA, so this and this are the same. So you've got dot dA, you've got dot dA over here. Surface integral, surface integral. Curl of E is equal to minus del del t of B. So that is what you have. Sorry, here. Minus del del t of B. Curl of E is equal to minus del del t of B. That is. Here we are looking at dynamics for the first time. So far we have talked about electrostatics. We have talked about in electrostatics, when a charge is fixed in space, it shows Coulomb force, which is a central force. Curl of that central force, which means it depends only on the variable or the coordinate r, spatial coordinate r, 1 upon q by 4 pi epsilon naught r squared r cap. We have worked with this kind of a thing. Curl of such a force field will be equal to 0. Nothing is wrong about that, except that that thing holds true only when the charge is static. But what happens if the charge is now moving, and moving in such a manner that the magnetic field, see, moving charge will produce a current. Fine, that is also okay. But if the current is steady, then the magnetic field will be fixed. What do I mean by steady current? Meaning that a current, there's a current passing through a wire, you have set up an observation post at some point in the wire, and at different points of time, you have taken your stopwatch. In 1 minute, what is the amount of charge that is flowing past? Whenever, at whatever time of the day you make your measurement, you find that the amount of current that is flowing past, within one amount of charge that is flowing past within that 1 minute time window is the same. So you say it's a steady current. Incidentally, that sort of a thing doesn't happen in the case of traffic flows. During daytime, around 9 o'clock, there will be a large traffic. Similarly, around evening, 6 o'clock, there will be a large traffic. But at 2 a.m., early in the morning, at 12 midnight, 1 o'clock at night, there will be practically no traffic. So you can see it. So that's an unsteady flow of cars. If you imagine cars to be like charges. So like that. But here, the current is no longer steady. Current is changing in time, current value. And if that is so, then the magnetic field will also be unsteady. It's no longer static magnetic field. We are no longer talking about magnetostatics. If we are no longer talking about magnetostatics, then del del t, time rate change of the magnetic field, will be non-zero. If the magnetic field were to be static in time, del del t of that magnetic field would have been 0. But here we have got a non-zero magnetic field. So no longer static B or E. We have encountered electrodynamics, no longer electrostatics or magnetostatics. We are now looking at electrodynamics. So curl of E is equal to minus del del t of B. Why is curl of E not equal to 0? Zero vector as it should be. Slight error over here. Page 116, I'll correct that thing. Just a minute. So why is this thing a non-zero vector? Because now we are no longer talking about static charges or steady current or any such thing. As a result, two of the things that you have studied when you studied statics, namely curl of the electric field will be 0 and the closed loop integral of the electric field would be equal to 0. Those things are no longer happening. So this is Faraday's law in Maxwell's equation. We will look at these things in greater detail later. So I hope you have understood the principle of Faraday's law. Changing magnetic field induces an electric field. So if the magnetic field is changing, del del t of B will be non-zero and that will produce and induce an electric field. And what about the minus sign? The minus sign is due to Lenz's law, which you would have studied at school. The change, the electric field so produced tends to oppose the change that produced it. So that is what it is. Okay, what did I tell you about the four Maxwell equations? The four Maxwell equations are, you have got two vector fields, namely the electric field and the magnetic field. You just have to do two things to each of these vector fields, namely take their divergence and their curl. Divergence of E is equal to rho by epsilon naught. That part is settled. We are no longer improving on that. That is also known as Gauss's law of electrostatics in the differential form. Then divergence of B is equal to 0. That happens because there are no magnetic monopoles. We have discussed that also. Okay. So the two divergence equations are settled. In statics, curl of E was equal to 0. But now when we bring in dynamics, curl of E is equal to minus del del T of B. Okay. So a little bit of modification has happened to the curl of E equation, and now we shall go into the curl of the B equation. Maxwell's correction of Ampere's equation. Could you just give me a minute, please? Thank you. Sorry. Thank you. Just a minute. Yeah, I'm back. So in statics, curl of E was equal to 0, as I have written over here, but we are no longer talking about statics, we are talking about dynamics. And now in statics, Ampere's law, Ampere's equation said that curl of B was equal to mu naught into J. What happens when you bring in dynamics over here? See, you can't have dynamics unless you have the presence of time. If it had been static, static means things are not changing in time. So time derivative would have been 0. But as soon as we bring in dynamics, del del T of B is no longer 0. So that is what happens over here. We shall have to examine Ampere's equation. Curl of B is equal to mu naught J. Is there a possibility of an explicit presence of time in this equation? Let us see how we get this thing. Curl of B is equal to mu naught into J. This is an extremely important discovery, theoretical discovery. What Faraday did was an experimental discovery, which was expressed in the mathematical language will give you this equation. I mean, curl of E is equal to minus del del T of B is a mathematical formula, but it is telling you something. What is it telling you? In plain English, it is telling you that a changing magnetic field induces an electric field. This is, in the English language, a changing magnetic field induces an electric field. And this is the same statement in mathematical language. Curl of E is equal to minus del del T of B. Just like you can express the same idea in English, Hindi, or Gujarati. So it is this thing. You have expressed the same idea, which is this idea that a changing magnetic field induces an electric field in the language of mathematics. Curl of E is equal to minus del del T of B. Okay. Mathematics is the language of physics. And why is mathematics the language? Why is it such a useful language? Because in physics we make measurements. So therefore, we need mathematical equations to be able to make systematic measurements. Anyway, so let us now look at Ampere's equation. Here it is. Curl of B is equal to, in differential form, of course, curl of B is equal to mu naught J. Very basic mathematical theorem of vector calculus, or mathematical identity of vector calculus tells you divergence of the curl of a vector field is equal to 0. Divergence of the curl of B is equal to 0. Okay. And then, but the curl of B is equal to mu naught into J. Therefore, divergence of mu naught J is equal to, mu naught is a constant, divergence is a differential operation. So mu naught comes out of the derivative. Mu naught into divergence of J is equal to 0. Divergence of J is equal to 0 means J, So mu naught into this thing is equal to 0. Mu naught is a non-zero constant. Therefore, divergence of J is equal to 0. And a divergence of, if a field is 0, then you can make the statement that it's a solenoidal field. So that is what happens when you have a steady current. Steady current. The current is not changing in time. At whatever, it's just like having a steady traffic all throughout the day, 24 hours, day, night, everything. Same number of cars are flowing past a traffic check post. That is not, that doesn't happen in reality, but I'm just giving you an example, hypothetical example. Now we look at a different angle in this thing. Look at a different issue. Consider a sponge. You know what a sponge is. Forget what we have got here right now. A sponge is something, if you put in water, it soaks in a lot of water, and then when you squeeze the sponge, the water flows out. Water is squirted out of the sponge. Okay, so here we have a sponge like that, except that this sponge does not contain water, as in H2O molecules, but contains charges, little dot point like particles carrying, let's say, positive charge or negative charge, whatever. And the total amount of charge contained in this charged sponge, electric sponge, if you would like to call it, is Q. Q at any point of time. So just like if you have a sponge full of water and you squeeze that sponge, water will then squirt out of that sponge. So as you are holding initially a completely soaked sponge in your hand and you are squeezing it. If you are squeezing it, then the water will flow out of the sponge. So at any given point of time, the water contained in the sponge is changing, right? Initially, there will be a large amount of water, and then as you're squeezing, water is flowing out. The amount of water in the sponge is reducing. Okay, so it is that here you have a charged sponge. It contains a whole big amount of charge initially, and then let's say somebody is squeezing this sponge, and the charges are flowing out. And so this is J, amount of charge flowing out through unit area in unit time. Amount of charge flowing out through unit area in unit time. Just like if I say that if I take a sponge and water sponge, that is, you dip it in a bucket full of water, it's come out completely soaked, you're squeezing it, and a little unit area of the sponge will show a certain amount of water has flowed out in unit time, 1 second, let us say. And so it is, instead of water, you're talking about charges flowing out because of the squeezing pressure that you have applied. Charge is flowing out in unit time through unit area. Charge flowing out in unit time is what? Current. So basically what you are seeing is current flowing out through unit area. If you integrate over the whole surface, then you will be able to find out the total current flux of the current. This current is a vector. In the last class, before the start of the last tutorial class, somebody was asking me, is current really a vector or not? Yes, indeed it is a vector, but we usually think of it as a scalar because we think of a current passing through a wire. A wire is a one-dimensional track. The charges have nowhere else to go except that. Therefore, we can afford to make our task simple by considering only a scalar point of view. But here you have a sponge. The charges can move out in all directions, just like a water sponge. If you squeeze, the water will flow out in all directions. So, so here we have current going in different directions, and here you'll have to be mindful about the vector nature of the current. Now, current flowing in charge flowing in unit time is current, and through unit area will give you J, which is the cross-sectional current density. Integrated over the whole area, here it is. If you want to integrate over the whole area, J being a vector, area is also a vector, dA is a vector. Integrated over the whole area, you first have to write down J dot dA. Both being vectors, you have to be careful. You'll have to take the dot product, J dot dA is the charge per unit time. Charge per unit time, underline, meaning we are talking about current over here, leaking out of the volume through dA area element. Area element dA area element. So that is basically the flux, current flux through this area element dA. Just like you have electric flux E dot dA or magnetic flux B dot dA, here you're talking about current flux J dot dA. If you take the full surface integral J dot dA, what will happen? What will you get? Follow carefully now. J, just look at it dimensionally. J is, I'll just end in a minute. I'll just end in a minute. Time is just, we just have 1 minute. J has got the dimension of current per area. Current per area into area will just give you current. So basically this integral will have the dimension of current and nothing else. And current is charge per time. J dot dA, full surface integral will just have the amount of charge flowing out through this whole electric sponge in unit time. So, and what is that? So as the charge is flowing out through this whole area in unit time, the amount of charge within that this sponge is also reducing. Instantaneously, the amount of charge contained in time t is capital Q. So basically J dot dA will be equal to minus d dt of Q. Notice that Q is reducing as time is increasing, right? Therefore, dQ dt, Q is the amount of charge contained in the sponge. It is reducing as time is increasing. dQ dt is a negative quantity in itself, but there's a negative quantity out, minus sign outside. Overall, this is a positive quantity. Anyway, we have run out of time. In the next class, which is on Wednesday, we shall discuss this point in further detail. If you have any questions, you may ask me. I'm stopping the sharing. I'll also stop the recording. Anybody has any question?